You ever just look up, see a plane cutting across the sky, and think, how on earth that work? I mean, it looks like this one massive, solid thing just hanging up there, defying gravity. But the truth is, it's not one thing at all. It's this incredible collection of engineering solutions, all working in perfect harmony. So let's do it. Let's peel back the layers and really see what's going on inside a modern airplane. Okay, so to get us started, I've got a question for you. What in the world does a regular old soda can have in common with a super advanced multi-million-dollar stealth fighter? I know it sounds a little crazy, right? But the answer, well, it's actually pretty amazing, and it gets right to the core of how these incredible machines are put together. Stick around, because we're going to uncover that secret deep inside the plane's skeleton. All right, so before we dive under the skin, we've got to know what we're looking at from the outside, right? Let's start with the big picture, the basic anatomy. Any plane you see sitting on the tarmac, it's really built around 5 main parts. Let's break them down. Okay, first up, you've got the fuselage. That's the main body, the big tube where all the passengers and cargo go. Then, of course, you've got the wings. They're the real stars of the show, generating all the lift to get this thing airborne. Now, that whole tail assembly at the back, that has a fancy name, the empennage. Its whole job is stability, keeping the plane pointed in the right direction. Underneath, you've got the landing gear, pretty self-explanatory, for moving around on the ground. And finally, the power plant. That's the muscle, the engines and propellers giving it all the oomph. So, we've got the parts. But how do these pieces actually work together to beat gravity? Well, it all comes down to this constant, invisible battle between 4 different forces. Think of it like a 4-way tug of war that's happening every single second the plane is in the air. Let's break it down. First, let's talk about the vertical fight. On one side, you have weight. That's just gravity, right? It's always there, relentlessly pulling the entire aircraft, the plane itself, the fuel, you, me, straight down toward the earth. And fighting back with everything it's got is lift. This is that amazing upward force generated by air rushing over the wings. It's a constant struggle, up versus down. And at the exact same time, you've got the horizontal battle going on. Pushing the plane forward is thrust. That's the raw power coming from the engines, just shoving it through the air. But the air shoves back. That's drag. It's the force of air resistance trying to hold the plane back, slowing it down. So it's forward versus backward. And here's the coolest part. When a plane is just cruising along nice and level, not speeding up or slowing down, those 4 forces are in perfect equilibrium. Lift is exactly equal to weight, and thrust is exactly equal to drag. It's this beautiful, delicate balancing act, all happening miles up in the sky. Kind of amazing when you think about it. Okay, so we get the forces. Now, how do you actually build a machine that can handle that constant battle? Well, now it's time for the fun part. We're going to peel back that smooth, sleek skin and take a look at the skeleton underneath. And trust me, that skeleton has changed a lot since the early days of flight. In the beginning, you had what's called a truss structure. Just imagine a strong but clunky internal cage made of tubes, kind of like a bridge, that was then covered with fabric. It worked, but it wasn't very aerodynamic. Then someone had a brilliant idea. What if the skin could carry all the stress? That was the monocoque design. And that idea eventually led to what we use today in almost every modern aircraft, the semi-monocoque. It's a hybrid, the best of both worlds, where the skin and an internal frame work together to share the load. And that brings us right back to our first question, the soda can. See, an empty soda can is a perfect everyday example of a monocoque structure. It's surprisingly strong, right? You can stand on it. But the second you put a little dent in the side, it just crumbles. An aircraft's stressed skin works on the same principle. It's not just a cover. It is a critical, load-bearing part of the structure. So this whole concept of a stressed skin, of using the skin for strength, it totally set the stage for probably the biggest revolution in building airplanes in the last half-century. And that was the shift away from good old aluminum to these new, advanced composite materials. So what even are composites? Well, at its simplest, you take super strong fibers, think carbon fiber or fiberglass, and you embed them in a kind of high-tech glue, which is usually an epoxy resin. It's a bit like reinforced concrete, you know? The fibers are like the rebar, providing all the strength, and the epoxy resin is like the concrete, holding it all together in the exact shape you want. Okay, now this is where things get really fascinating, because composites are a classic case of pros and cons. The upsides, they are incredible. They're way lighter than metal, they don't corrode or rust, and you can mold them into these beautiful, smooth, aerodynamic shapes that are impossible with aluminum. But the downsides are just as huge, and the number one problem is a real shocker. Damage to composites can be completely, totally invisible. So let's really dig into why that's such a massive deal. Picture this. A mechanic is working on a plane in a hangar and, oops, drops a heavy wrench right onto the wing. It happens. Now, if that wing is made of aluminum, you get a dent. Not great, but at least you can see it, right? It's obvious. But on a composite wing, that same little low-energy impact creates a much, much sneakier kind of problem. Yeah, because from the outside, the surface might look totally perfect. You might not even see a scratch. But underneath that smooth surface, the shock from the impact can actually cause the layers of carbon fiber to separate from each other, to peel apart. It's a thing called delamination, and it can spread out like a cone under the surface, creating this big hitting weak spot that nobody can see just by looking at it. And that right there, that is the single most important thing to understand about composites. The most dangerous damage can be invisible. Just think about that. It creates a huge challenge for maintenance crews. They can't just rely on their eyes anymore. They have to use special tools like ultrasound to find damage they literally cannot see, just to make sure that plane is 100% safe to fly. So, we've gone from the outside in, right? We've looked at the big parts, the forces, the skin, and the skeleton. For our last stop on this tour, let's head to the brains of the operation, the cockpit. Let's see how the pilots actually fly these incredibly complex machines. You know, if you look at an older plane, the cockpit is just a sea of round, steampunky dials and gauges. It's honestly a little overwhelming. But today, most modern aircraft have what we call a glass cockpit, and the change is night and day. Instead of all those individual gauges, pilots get a big, clean primary flight display with all their critical info in one place and a multifunction display for everything else. This isn't just about looking cool. It's a massive leap forward in safety. It cuts down on pilot workload and lets them see the big picture at a glance. So there you have it. From those early fabric-covered truss frames to these intelligent composite structures, and now to digital glass cockpits, the story of the airplane has always been one of relentless innovation. Which, of course, leaves us with one last big question. When you think about what's coming next, things like self-healing materials, maybe even AI pilots, what do you think the next great revolution in how we build planes is going to be?